Yes, Shambhavi. Hello.
Hey, yeah, ma'am, I'm here.
You can start recording.
Okay, ma'am. Sorry. Yeah, before I start recording, just making it clear that this will be further evaluated and then we'll get back to you once we have the feedback. I'll just start the recording. If you can please start with a brief introduction about yourself, and then you can go ahead with the demo that you must have
Okay.
prepared, ma'am.
Any of you are the subject expert?
Uh, ma'am, we handle a plethora of subjects. So, uh, we are no one here is exactly subject expert, but
Okay.
yes, this will be further evaluated by the subject experts so that.
Okay. Okay. Fine. Yes. So, good morning, Shambhavi, Amina, Shreya, and Kishore. I'm Dr. Harshlata Petkar, working as assistant professor in Department of Language Technology and Language Engineering at Mahatma Gandhi Antarashtriya Hindi Vishwavidyalaya. Basically, it's a central university, and just a minute. Yeah, 1:15. Sorry to interrupt. So today's demo, I'm going to give a demo on dimensionality reduction and a few of the introduction about the singular value decomposition. Yes, am I audible properly, Shambhavi?
Yes, ma'am, you're properly audible. And yeah, please go ahead with sharing your screen.
Sh- Is it visible?
Yes, ma'am, this is visible.
Okay, so let us talk about the dimensionality reduction. Uh, See here, when we talk about the computer science, or let us suppose the theoretical computer science, we started its journey some around in 1960. And in 1960, we used to learn about the theoretical computer science in terms of the compiler designing and theory of automata. Then it comes to the 1970s, it is all somehow we started introducing algorithms, and now we are in a position that we are having a piles of data, we are having communication devices, we are having sensors, we are having webs, we are having websites, and social media and so on. So that pile of data won't be handled with the traditional algorithms, so here it is the machine learning algorithms comes in picture. Basically the concept is we need to learn from the data, and the data is of a variety that's all basically unstructured data, and that data would be in form of a text, in form of a image, audio, video, time series data, and so on. So first of all, before going into the detail about the dimensionality reduction, let us talk about the dimensionality first, what exactly it is. Each of the input variables or attributes or features are called as a dimensionality. Each data or each data set is having its characteristic or features, we call it as a dimension. And the dimension, very easy example, to make it understand, let us suppose we are having cookie, and we have the four dimensions like shape, then color, taste, and price. So these are the dimension of that data, dimension of that cookie. In the same way, we are having some grayscale images of 50 by 50, so we will be having 2500 dimensions. And we are having the RGB colored image, we will having the dimensions of some around 7500. So at this stage, when it comes to the dimensionality and the data with the high dimension, means having so much of features, so many features, and the observations or its corresponding values would be very less, and the dimension of the data would be more, then we call it as a high dimensional data. So this high dimensional data definitely is going to be indicated by p is greater than n. So p is greater than n means p are the features and n are number of observations over here. So this is the high dimensional data, and such kind of situations nowadays are of course it's very frequent to get such kind of situations. So ultimately we lead to the one phenomenon which is called as curse of dimensionality. So this curse of dimensionality, definitely why it is curse, that we need to reason out, that we need to find out, and what are the problems or challenges with that high dimensionality will be there. We have to find out, and then we will come to the solution. We will discuss the solutions. Now see here how the curse of dimensionality really visualized. Let us suppose we are having one dimensional data, same cookies example. So at this point of time we are having the four dimensions we are having. So the four dimensions are four features, but when we try to choose from a single dimension, we will be having the four choices. Like if you want to go for a test, then we have to go for the four type of tests, suppose salty, sour, sweet, or some other test. So here 2 by 2 matrices or 2 by 2 dimension will be indicating we are choosing out of the two dimension. We are choosing out of the two dimensions. We are choosing the test as well as we are choosing the color. If we will be choosing out of the three dimension, then we will be having the test, and we will be having the color, and maybe we will be having the shape. So you can understand over here we are having the four choices. We are having now 4 by 4 16 choices, and we are having here 4 by 4 by 4, that is 64 choices. So the dimensions to represent that particular cookie or a particular data will be increasing exponentially. So this is how about the dimensionality work or increase in dimensionality works. So basically when it comes to the problems discussion, that problem discussion is first of all we have to understand if there are so many dimensions, then the intuitively we will be getting the notion that we need a high number of samples. We need high number of samples to represent that particular feature, particular data set in a particular dimensional space. Then we will be having another problem, that when we are having high dimension, then the data is ultimately is going to be very sparse, then highly correlated, and we are see that so many data we are having which are redundant. So let us understand the sparsity first. In sparsity we will be having the features with most of the time we'll having zero data over there. So these zero data may indicate that there are redundancy. There are redundancy in the sense, let us suppose get the real-time example of recommendation system. In recommendation system, we visit e-commerce website for any products. So that commerce website will be having maybe thousands or millions of products, but user will be visiting the products which of their own interest. So it may be the case that we are having the matrices, we are having matrices or a vector where we are having only few values which are one or which are enabled or which are visited, and rest of the values or rest of the products which are not visited would going to be zero. So like this we will be having the very sparse data. Those sparse data, then which are highly correlated data, which are redundant data. So huge dimensions or high dimensions are definitely going to consume a lot of space. So computing is expensive, and ultimately if the computing is expensive, space is more, then there is a time constraint. Time will be more to calculate the intended result. So here this is how about we are talking about the problems arised with the dimensionality or high dimensionality. So this manifestation is, again, we have discussed, or let us suppose I will reiterate that the distance will be more in a data points. We will be having dense, not dense much, but we will be having the sparse data over here. And to represent a single data set, we need more and more features, more and more dimensions, so we need more data. So the thumb of rule will be, at least we need to have 5 samples to represent the particular data point. So next comes the overfitting. Overfitting is when your data, or let us say when your model, ML model, will work on a training data appropriately. It works fine with training data appropriately, but when it comes to the testing data, it fails. So testing data means the model is not able to generalize, model is not able to properly work on the testing data, and it overfits the model. So work on training data only properly. And another point is combinatorial explosion. As we have discussed about the curse of dimensionality in the initial slide, we are having the curse of dimensionality which extend or which expands exponentially. So this is how we are talking about the curse of dimensionality, and of course the computability is one of the problem. Now see, this curse of dimensionality again arises one phenomenon which is called as a Hughes phenomenon. Hughes phenomenon or a curse of dimensionality are somehow similar terms. Here we could say that in a Hughes phenomenon, it is given, you could understand here, the classifier performance against the dimensionality. At that point, if you try to observe this graph, here the dimensionality is going to increase, as well as the classifier performance is going to increase in this way. But reaching to this optimal situation or optimal point, the dimensionality is going to increase. Here the dimensionality is going to increase, but the classifier performance is going to decrease. So at this point of time, having a high dimensionality, with this notion, with having a high dimensionality, always it is not favorable to the machine learning models or classifier. So we need to have some optimal dimensionality, or a dimension of our interest where the classifier performs very well and it won't degrade the performance like this swiftly. So here let us talk about these things, and we will let us talk about the addressability of the dimensionality reduction. Now it is, of course, come to the point that dimensionality reduction is going to be a nightmare. It's very critical problem, because we are dealing with the real time data, and if your real time data fails at the real time applications, then it would be really a problematic. So why we will give the solution to the high dimensionality, why we need to reduce the dimensionality? So basically reducing the dimension is one of the solution, but why we need to do that? See, one is interpretability, then visualization, then we need to reduce the overfitting, so that our machine learning model won't imitate the training data, it will equally work with the testing data. And the scalability, most of the dimensions as increased in a particular application, it won't scale properly. So scaling will be done by decreasing, by reducing the dimensions. Also see, if we want to visualize the data in terms of the high dimension, it is not possible. So possibility is reduce it into the two-dimensional or a three-dimensional data, and then you can visualize it properly. And human being cannot interpret the data if they are having the high dimensions, but interpretability is easy when we reduce the dimensions, right? So these are the reasons why we try to go for a dimensionality reduction. And then there are several options that how we will be reducing the dimensions. There are two techniques or two approaches. One is feature selection, this is feature selection, and another is feature projection. So there are several names: feature extraction and feature transformation for this feature techniques. So feature selection is somehow it names itself suggests features will be selected uh, out of, or handpicked we would say, out of the plethora of features. We are having several features and we need to keep the features which are best for our model, or best favorable for our model. So how we will do that? That's a question. Basically, this feature selection method, it needs to know the problem domain properly. You see, if you don't know the problem domain, what exactly problem is or what are the underlying details, then we cannot pick the best features. We will pick the features which are not at all important to that domain. Then definitely here our dimensionality reduction will fail. We won't be getting the desired result of a classifier, and the classifier will not classify. There will be more and more false positive values. So these are the failure reasons. So understanding the problem domain is a key point while uh, approaching to this feature selection. And another is feature extraction. Feature extraction is somehow something different. Here we try to transform the feature, transforming the feature from the original set of features. So here let us suppose we have the features like this, we are having the vectors like this. Now we will try to transform it in a different directions like this. So here we have perform the rotation. So that is a one way of transformation. Now this transformation has got the two approaches, sub approaches, that is linear and non-linear. And the non-linear method we will be talking about, that is SVD, singular value decomposition, and principal component analysis. So there are several linear methods to discuss, and as well as non-linear methods. So non-linear methods are basically work when we are having the complex problem. We are having some problems in hand where the linear methods fails. So usually that non-linear methods are kernel PCA. It is given in this slide. Kernel PCA, TSNE. So TSNE is a T stochastic neighborhood estimation. Autoencoders, SOM, that is self-organizing maps, ISO maps, and UMaps. So these are very complex methods and it work with the data where the linear methods fails. Now let us start discussing the singular value decomposition. Here this singular value decomposition is one of the very popular method of feature projection, or ultimately the dimensionality reduction. Here singular value decomposition will start by decomposing the matrices. Decomposing the matrix A. Basically, let me tell you one thing over here, that before going to the singular value decomposition, the learners should understand, or it is understood that learners are well aware about the matrix concept or a linear algebra concepts, like what is singularity, orthogonal matrix, what is dot product, what is diagonal matrix, what is the multiplication of matrix, and etc. So here singular value decomposition, let us suppose this method works with the linear algebra concept. Here we are having the matrix A with dimension n by p, n rows and p columns. So it is decomposed in the three low ranked matrices U, S, and V transpose. So basically here the A n by p, U n by n, S n by p, V p by p. So just observe the dimensions over here. Here this is the rectangular matrix. Originally this A is a rectangular matrix and you can observe here that A is having the similar dimension as that of the S n by P. So this is also a rectangular matrix, as well as this rectangular matrix plus it is a diagonal matrix, where we are having the eigenvalues. Better we will initially talk about the eigenvectors which are placed diagonally. Now u n by n, it is called as SL, that is left singular matrix, and VT P by P. So this is the SR, we call it as a right singular matrix. Now, before understanding all these things, we have the calculation of eigenvalues and eigenvectors, where we talk about the A multiplied by AT transpose A. So how it would work really? Let us talk about the notion of the matrices. So see, A is a rectangular matrix. So I will write here like this. A is a rectangular matrix. Suppose it's having dimension 2 by 3, and we will transpose it. So A transpose will be 3 by 2. So resultant matrix after multiplication, we are having the square matrix which is our 2 by 2. In the same way, when we talk about the A transpose T, so we will be calculating the 3 by 2 matrix multiplication with the 2 by 3 matrix multiplication. Now the product of these two matrices will be again a rectangular matrix, which is 3 by 3. So this is a notion where we are getting the rectangular values, and with this notion, the singular value decomposition will calculate the eigenvalues as well as eigenvectors, and the singular, rectangular and diagonal matrix which will be having the eigenvalues, say delta 1, delta 2, 0. So these are the eigenvectors. These are the eigenvectors. Now here u will be giving you the rotation, V transpose will be giving you the rotation. They are form of a transformation, right? As we talked about the feature extraction or a feature transformation method of a dimensionality reduction, we have to transform the data. So rotation, then this rectangular diagonal matrix will give you the scaling effect with the value of this eigen vectors. Now eigenvectors of the matrix, they are the directions of the maximum spread of a variance of a data. Now spread of a variance of a data means these data will be having the high variance. So first of all, going into the detail much, let us understand the variance concept. So there are two type of a concept, bias and variance. Variance is where when we talk about the machine learning model, we will be having the two types of data. We are having the actual data that we really know, and we are having some predicted data. So that is what the model predicts. So variance is the predicted data is spread, they are apart from each other. So if they are more apart from each other, then we would have the high variance. We are talking, just remember, we are talking in terms of the predicted data. And if the data very close to each other, then we will say that we are having the low variance. Now this eigenvectors will give you the spread of variance. We will choose such eigenvectors basically where the values are more, so that high variance will be there and the low variance data will be get discarded. Now this decomposition will allow altogether, it will express the original matrix in form of a linear combination of low ranked matrices. So So this is the single value concept of a singular value decomposition. See, this transformation has been given in this way, where we are having the v t, that is v transpose. V transpose will transform these two vectors into these two vectors, and then here it is a sigma. Actually this is s. Few of the authors will write it as a sigma and few of them address as a s, which is a diagonal and rectangular matrix. So this diagonal rectangular matrix will give you the variance of the data. So this is what we are getting. We are having this vector will get scaled, will get elongated, and we will be having the transformation like this scaling effect, and again you will be having the rotation. So in this case we are rotating our vector in this direction. Fine. So this is the visual representation of singular value decomposition, where we are transforming our matrices, that's a rectangular matrices, into the singular values with the u, s and v transpose. Now coming to the another method, that is principal component analysis. Why SVD and PCA both need to studied all together, not parallelly, one by one, because principal component analysis takes the single value decomposition value or the eigenvectors value which is found during the calculation as an input in a PCA this technique. Now this is called as a classical, let us say, the application of a SVD. Classical example, it is classical example as well as the application of singular value decomposition. In the singular value decomposition, we get the eigenvalues and eigenvectors, and once we obtain those vectors, that vectors will be the input to the principal component analysis to find the principal component. So basically this principal component analysis is a dimensionality reduction which is very common and very effective. So what exactly we are doing over here? We are having the multidimensional data and we try to reduce its dimension as that of our considering the principal components of those data sets. So here let us talk about what exactly the principal component analysis is. It's just a visual presentation. If we go into the mathematical detail, it will take too much of time. So PCA definitely will be overcoming the overfitting problem. Now the step by step algorithm, we would say, of a principal component analysis is we need to calculate the mean, then covariance matrix, and here SVD comes in picture. Singular value decomposition calculates the eigenvalue of covariance matrix, then we calculate the vectors, and then we calculate or compute our first principal component, and then we take the geometric mean of this first principal component. So first of all, having the visualization of what exactly principal component is. See here, this is the data. This is two-dimensional data. Let us have consider two attribute 1 or attribute 2. Attribute 1 may be the user, attribute 2 may be the visited product, attribute 1 may be your salary or age or your qualification or salary or something like that. So many data will be there. Some biological data might be there, or astronomical data, or with the prediction data. So see, these two attributes are there, and these two attributes are spread like this. You can visualize here two-dimensional two attributes are spread. But here when we talk about we will observe this line. This line will show that each and every data point over here, see, each and every data point will try to, here it will try to touch the data. it's very near to the line, they try to touch the data. So that means what exactly? They try to touch the data means it is suffering from the problem of overfitting. The data is overfitted. Usually this data, when it overfits, so this data may be designated like this. It will try to touch each and every data. So this is the overfitting problem, and this line tend to overfit the model. Now here this PCA will overcome the problem of overfitting. That's the thing. But how it will do? It will do it by reducing the dimensions. It will reduce the number of features, it will reduce the number of attributes, and it will shift whole thing from high dimension to low dimensional space. Now see here how this is going to view principal component analysis. Here we are talking about the views. So we will be having some view over here. It may be orthogonal views. View will be a kind of a plot, where once we will be having such kind of view, we will be having the picture of a one dimensional space as a principal component analysis 1, PC1. So definitely this is one view. We will be having another view as well. Actually when it comes to the view can be equals to the number of dimensions. So two dimensions are there. So here two views can be calculated. We calculate the two views, in turn they will give a principal component analysis number 1. Principal component 2 will look like this. See here. So this principal component analysis will look with this view, and it will look like this. So we are trying to do the geometric mean. We will take the principal component, and then we will calculate overall, we will calculate the principal component, and the dimensionality will be reduced, and it will help in solving the problem of overfitting. It will help in visualization as well. So how we will be visualizing, or how we will be looking into the three-dimensional data or a two-dimensional data, and how the dimensions are spread across the x, y and z axis in a three-dimensional data. So let me visualize, or let me show you this TensorFlow project which is by Google. One is project.tensorflow.org. So let us check. Yes, yeah, yeah. Fetching the tensor's value, parsing metadata, computing PCA. You just observe this computing PCA, how the PCA has been computed over here. It is all automatic, and the code behind this complete project can be explained later. Here you could see that the dimensions are 200. Here dimensions are 200, but this PCA has been applied, and this PCA have the several components, basically three principal components, along with the x, y and z axis, component 1, 2 and 3 with the variance 1 to 10. Here it is a variance, percentage of variance 1 to 10, and again the second component have the variance, and as well as third component have the variance. So here you can look at how this data has been spread, and this data is basically tensor data with the method word to vec in short. So word to vec method will convert the textual data into the vectors, and that vectors will give you the contextual meaning, or in a complete linguistic term, it is indirectly a shallow parsing, and gives you the semantic role labeling kind of data as well. So here, see, I will, this is a three-dimensional data. You can look at this axis, thin lines are there to represent the axis, and if I will just discard one axis, then the data will be two dimensional. Here the data will be two dimensional. Each and every data points, somehow 10,000 data points are there, and each and every data points represent a word, and word itself having the two dimensional vector. See here, wherever I try to move my cursor, there are words: HTML, specimen, hat, hide, adventure, etc., etc. So this is just a example that how the dimensionality will be here. 200 dimensions are there, and how the dimensionality will be reduced with the help of PCA by calculating the principal components. And if we again reduce the principal component along with the 3 dimension to 2 dimension, then the data will look like this, and if we'll include the third dimension, the data will be look like this. Yes, so this is how. Yeah, so this is some of the bibliography section. Basically it's not reference, it's a bibliography. Thank you very much.
Thank you, ma'am. Thank you so much for presenting to us. Our community team will get back to you with the feedback in 2 to 3 days. Thank you so much for presenting to us, ma'am, and have a great day.
Okay, thank you, Shambhavi.
Thank you, ma'am. Bye.